Write the three equivalent Lewis structures for the SO3 molecule that conform to the octet rule and describe the resonance hybrid of the molecule. So we're going to go off and talk about sulfur trioxide. That's a nasty molecule if there ever was one. But it's a good example for what we want here. How many valence electrons are there in sulfur trioxide? 24. Excellent. 4 times 6, right? They're all in group 6. So there's 24 electrons. So we will just simply take this sulfur. I'm going to put the sulfur in the middle. Why is that? Less electronegative goes in the middle. Okay, so then there'll be the oxygens on the outside here. So that's the topology. And we'll take our 24 electrons and we'll make 3 single bonds. Okay, so 24 minus 3 times 2 is 6. That's 18 electrons left. Okay, so we'll put them on the oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, 18 minus 18 is 0. Nothing left to put in the middle. But the sulfur doesn't have an octet, so what do? We make a double bond, a multiple bond. We make a double bond by taking a lone pair off one of the oxygens and putting it in to make a double bond. There are 3 different oxygens. How do we determine which one is which? We can't. They're all equally probable. So we'll just take that one and we'll put it here, and that'll make a double bond right there. So I'm going to reproduce this down here. We have double bonded oxygen. We have a pair of single bonded oxygens. Now at this point, I need to ask you a question. Are there resonance forms for this molecule? How many think there are? Okay. How many think not? Okay. Yeah, he thinks not. Okay. What is a resonance form? It's a Lewis dot structure that differs not in the position of atoms. All the atoms are positioned exactly the same way, but in the position of electrons. Electrons. So if we can deal with movement of electrons here without moving the sulfur or the oxygens, we have resonance forms. And obviously we can, because we could have made this double bond here, or we could have made it here. So let me put it over here to start with. That'll leave 2 pairs of electrons there. We'll leave a single bond oxygen here and a single bond oxygen down here. Okay, so that's the second possibility. The third possibility is put the double bond down at the bottom. We're just moving electrons, nothing else. We're not moving the atoms. Are there any other resonance forms? Keep in mind, resonance forms have to obey the octet rule, and these all do. Okay, so what is a resonance hybrid of this set of resonance structures? Well, we have to represent that there are 3 single bonds that stay in one spot and 1 double bond that moves all around. So the hybrid will have dotted lines to show where that pair of electrons that makes up the double bonds go. It goes equally to all 3 bonds. All the electrons move around, delocalized equally to all three bonds. Everybody see that? Anybody have a question about it? Then what's the bond order? How many pairs of electrons involved in the bonding? How many? One? Okay, let's work it out. Let's count. We can use any one of these resonance forms to do it. I count 1, 2, 3, 4 pairs of electrons involved in the bonding. 2 single bonds and a double bond. So the bond order is 4 pairs divided by how many links? 3. I heard you say it. 3 links. The sulfur and this oxygen, and that oxygen. So the bond order is 1.33. It's 1 1/3 bond. That's even more bizarre. Is there any evidence for it? Is there any evidence for it? There is. We're going to talk about bond distances shortly. But the stronger a bond is, the higher its bond order, the shorter it is. So there are molecules known that have sulfur-oxygen single bonds. They're long. There are other molecules known that have sulfur-oxygen double bonds. They're shorter. Where do you think the sulfur trioxide one is? It's in the middle.